Okay, AP Calculus, we're going to get rolling into Chapter 2 here. I'm actually re-recording this video now. I had it down once, and for some reason the sound, which had been working, stopped working. And so it looked like the original video that I made only really covered about the first two slides right here, and Part 2 looks like it's up and running beginning on slide number 3. So we'll try to make this one pretty quick. So in Section 2.1, we start talking about this really important word right here, guys. That's the first main thing that we cover here in a Calculus 1 class, and that is the idea of limits. Now, I'm pretty sure you guys learned about, and maybe you even remember a little bit about limits last year in pre-calc. But good for you guys here. We're not going to assume that you remember anything from last year. We're really going to go back to square one and just kind of dive into these at a very fundamental level. A couple of other concepts going along with it here would be the concepts of rates of change, which we'll define here very shortly, and eventually we're going to get into a concept of tangent lines as well. And my guess would be you guys think you know what a tangent line is, but you're only about half right. But we'll get to that a little bit later. First, we want to start off with a definition right here that really isn't super important here that you have this memorized, but a difference quotient. So a difference quotient, if you break down the words, difference means that we're going to be talking about subtraction, and quotient means that we're talking about division. So a difference quotient is simply a quotient of two differences. So a lot of things out there in the world could be a difference quotient, but the most common example, one formula that you guys have been using a ton for probably the last 5, maybe even 6 years in math, that involves subtracting two different differences and then dividing, maybe you thought of it already, is the formula you've been using forever for slope. The formula for slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So what are you doing there? You're taking the difference of two y coordinates in your numerator. Then you take the difference of two x coordinates in your denominator, and then you divide those differences. That, everybody, is an example of a difference quotient. Now, it's sometimes more efficient to write it with the Greek letter delta there, which we use all the time in math and science, to mean change. So the slope formula, of course, is change in y over change in x, and that would be just one example of a difference quotient. That's really about as much as we're going to say about it right now, but we use a difference quotient then to get into this big concept right here. Now, back to the title of this section, we're going to be discussing rates of change, and notice the word rates is plural. There's two different kinds of rates of change that we are interested in. And the first one, and lucky for us, the far simpler one to understand and to find, is what is called an average rate of change. And so I made up this abbreviation here. I'm sure other people did too. AROC is something we're going to use a lot. Now, the average rate of change, and I should be specific here, of a function called f of x on a closed interval starting at a and ending at b. This is asking the question that if a function changes its value over time, how quickly does that value change? How fast, how slow, does it increase, does it decrease? So when we're talking about that, everybody, and we want to know how you get, for example, from point A to point B along some particular curve right here, so if I said that was point A and this over here was point B, the question would be, what is the rate of change here on average in getting from your starting point to your ending point? Well, I'm hoping you guys may have heard this somewhere along the way. A rate of change is really the slope of a line. So the formula for average rate of change is going to be the same as the formula for slope of a line. We're just going to bend it around a little bit to our purpose here. Rather than putting y2 minus y1 up on top, we're talking about a function called f of x. So instead of y's, we're going to do f's. And we want to measure this thing at the end point first. So b is the right endpoint of our interval. F of b, therefore, is the y value where this particular journey ends. Minus now the starting y value, which is going to be measured right over here. That y value is going to be f of a. So I'd really like you to think of this as ending y value minus beginning y value. Down on the bottom, we do the same thing, but for x values rather than y values. And the x values are given to us right here in the interval. Ending x value is b, and the ending a value right there, the beginning x value is going to be a. So this is a formula right here, guys, that's really identical to the slope formula here, but we're using f instead of y, and we're using these a and b values instead of x. Another way you could write that, if you were so inclined, is to put not a delta y, but a delta f up on the top of that function. And then down on the bottom, let's take a look. The way that I've written this function, that right there is important. That x tells you that these are x values. So technically that probably should be delta x down there on the bottom as well. But I do have to warn you guys, what we're going to see more often than any other type of problem in this chapter is a function here dealing with an object in motion measured over time. So very often, instead of these being x values, those are actually going to be t values there. So change in f over change in t, and that means change in time. So however you want to do that, that numerator could be delta f or delta y. The denominator could be delta t or delta x. It just kind of depends on the problem. And we're going to go ahead now and write one thing more down here that we're going to need before we move forward here. This formula here for average rate of change, and this is really the version of it that you need to know, is good for one other thing. If you take a look at this little curve that I just magically made up right here, and maybe it does a lot more exciting things. Maybe it goes up and then comes back down and then comes up again, and maybe on the left it just goes all the way down. I'm just guessing here. But if you'll notice, I chose 2 points on that curve. Now, I picked them at random, but in problems that you do, like the next example, those values will be given to you. Like in this case, 0 and 9. And this one, oh, that looks fun, negative pi over 3 and 11 pi over 3. Now, when you choose 2 points on a curve, like I've done here with A and B, you've all passed geometry, there is one and only one line that passes through both of those 2 points. And that line, we would say, is defined by those 2 points. So if I were to go ahead and draw that line out forever, there is a name for this type of line, everybody, and I don't think it's been mentioned yet here in this section. But a line defined by 2 points in a curve is called a secant line. And what we found right here then, guys, is the slope of that secant. So this same formula here for average rate of change can also be used to find the slope of a secant. And while we're at it, I should probably go ahead and define this formally in our notes, guys. Our definition, that wasn't well drawn, our definition of a secant, everybody, is simply this. It is a line defined by 2 points on a curve. Now that might be slightly different than the definition that some of you guys already had in mind. When you first learned about a secant, it was back in geometry in the chapter that you did on circles. It's not a very good circle, but okay, close enough. And what you guys learned in geometry is that a secant line, maybe you remember this and maybe you don't, is a line that passes through a circle and hits it twice, once here and once here on the way out. And what you might also remember from geometry is that a tangent line is I did a pretty good job there. A tangent line is one that only hits the circle once, and that would be a tangent. Now, for that reason, a lot of people make it through geometry and Algebra 2 and pre-calculus thinking that the definition of a tangent is a line that crosses a curve exactly once. And that's what happens in this example. They also think that a secant is a line that crosses a curve exactly twice. And that's what happens also in this example. But I drew this weird case here back in the day, in this example, to illustrate a point right here, guys. The way I've drawn it, there are actually, let's see, how many points of intersection now between the secant line and the curve? A and B. There's a third one right over here and a fourth one right over there. This is still a secant line, even though it intersects the curve more than twice. So I'll have you come back to this definition right here. That green secant line was defined by these 2 points on the curve. And what happens after that is incidental. I don't really care if it never crosses the curve again or if it crosses it a whole bunch of times. In fact, if you think about the example of a sine or a cosine wave that would look something like this, you could define a secant by this point right here and this point right here. Now there are your 2 points of intersection. But if you keep going, this is going to cross your curve, well, if I drew it right, how many times? Potentially infinitely many. All right, so it's really just the definition here that matters. And by that I mean this secant line was defined simply by 2 points on a curve. And a little bit later on in this section, we're going to redefine what a tangent line actually is, and it's not quite what you guys might think. Okay, so this is the formula here for average rate of change. It is the same as the formula for slope of a secant. So whether a problem is asking you for AROC, average rate of change, or slope of a secant, you guys are going to use this same formula here to answer both questions. And that's as far as I'm going to go with this video, because on the next one, which I think the sound is working on, we pick it up right here on example 2A. So we'll cut this one off here.